Today, I would like to share my recent research, the group-assisted multiple testing of multiple hypotheses appearing in groups, and an acronym for this method is called GATE. So this large-scale multiple testing is an integral part of statistical investigation toward making final discoveries in the modern data-centric scientific studies, especially once the data act we're considering is really big data set. A paradigm shift has been taking place from single to multiple groups of hypotheses, so it is very easy to see that the group structure exists in many applications in the big data. Often, enormous computational challenges associated with big data force one to separate huge-scale testing problems into computationally feasible sets or chunks. So this paradigm shift has brought in new theoretical and methodological challenges. So in this talk, I just want to provide two motivating examples, and then that will start with our method. The first examples is for the adequate yearly progress, the AYP data. In this data set, we compare the academic performance for the socioeconomic advantaged students against the socioeconomic disadvantaged students. And the other one is from the satellite image data for the normalized difference vegetation index. So for the AYP, and this in the 2001 the No Child Left Behind Act required that each state shall establish a timeline for adequate yearly progress, and this is established by President Bush. So this AYP is a measurement defined by the U.S. federal to determine how every public school and school district in the country is performing academically. So this can be used as diagnostic tools to determine how the financial resource should be allocated. And then one of the goals of this AYP study is to compare the successful rates in math exams between these two different groups of the students. And the data we are considering is from California in the year of 2013, and then there are altogether 41 and 8 elementary schools which are under the consideration. And we compare the success rates of both the socioeconomic advantaged students and socioeconomic disadvantaged students, and then we calculate the p-values. So however, for these schools, they are not just simple hypotheses. These schools can be naturally grouped according to the school districts. So altogether, we have 701 school districts. And therefore, this hypothesis actually can be placed as these two into this group structure. Okay. And for this hypothesis, actually, the number of schools within these districts varies from 1 to 277. So this number is not uniform. So there exists strong heterogeneity among the group size. And then secondly, the sparsity exists among schools within each district as well as among the school districts. So that means not all the schools will be significant. Secondly, even the school is significant does not imply that all the schools within this district are significant. Okay. So another example is from the NDVI data. So this is satellite imaging covering in the East Africa. And then we consider more than 50,000 sites. And for each site, there is a spanning of 8 km times 8 km grid of land. And then we have the data which is the time series for each site. And that is twice a month we have the data from the year of 1982 to 2006. And then for each site, actually, each year can be split as 4 different seasons. And therefore, altogether, we have more than 200,000 time series. And then we want to identify the combinations with significant increasing or decreasing trend over the last 20 some years. And then we can calculate p-value for each site and for each season. And then the group structure exists at 2 levels. So for each site, there are 4 p-values corresponding to 4 seasons. And secondly, the sites can be grouped spatially according to the geographical distance. And then for this most motivating example tells us that how to incorporate the underlying group structure in the statistical modeling seems to be an important question, yet challenging. and then how to construct a method controlling the first discoveries, not only for the total one, we also want to control the first discoveries between the groups as well as within the group. So these are all challenge questions which has not been addressed in the existing literatures. So the method we are going to provide is called GATE. So number one, we model the data, and especially we model the hidden state corresponding to the group and within group level, which are denoted as theta G and theta GJ according to the following model. So on the group level, for each group, there is a certain chance pi 1 that this group will be significant. And then if this group is not significant, then all the hypotheses within that group will be formed null. On the other hand, when the group is indeed significant, and then for each school within that school district, it follows a Bernoulli distribution. Okay? And then we assume that this X, the data given the hypothesis theta Gj, follows the two-group mixture model. And assume this, then we can show easily that the posterior probability that this hypothesis theta Gj is from the null given the data can be decomposed as these two parts. One is considered as the group-wise between group local FDR scores, and the other one is given that the group is significant, what is the chance that the school itself is not significant? And eventually we can propose this method which appears to be a little bit more complicated. Okay, so this is a two-stage method. Number one, for each group, we want to go into this group and then we order the local FDR scores from the smallest to the largest, and then we choose the largest number RG such that the cumulative average of the first RG smallest local FDR scores is less than or equal to eta, which is less than alpha. And then we mark this hypothesis for the potential rejection. So this guarantees that within the group FDR level is controlled. And secondly, we go to the group level. So for each group, we calculate the quantity eta G as well as a score representing the whole group FDRG star. And then we order them increasingly and then find out what is the maximum number of groups to be rejected. And eventually, all the marked hypotheses within this rejected group will be ultimately rejected. So it is guaranteed that for this method, the FDR, the posterior total FDR can always be controlled at alpha level. And then we can apply this method, for instance, to A by P data. So as we said that we have 4106 elementary schools, and then we have 701 qualified school districts. And then we apply this different method. For the proposed one, GATE, we can discover 707 schools which can observe a significant difference between those two groups of students in terms of the passing the math test. And then the number of identified school districts is 219. And then for the other two methods, like the Sun and Kai's method, SC, and adaptive BH, so number one, they have a small number of the schools to be rejected. Number two, they do not have any decisions on the school district level. And when we increase the alpha level to 0.1, we still can see the similar pattern. So the proposed one is always the best. Okay? So this is just one of the applications, but there are so many other applications that we can potentially incorporate this GATE. For instance, when we consider genes, they can be grouped according to the pathway gene ontology. In the SNP-VOX analysis, the hypotheses are grouped according to the SNP-VOX combination. And then group structure can exist, for instance, due to covariate, and in the variable selection, like group lasso, and then we can use this, there's a potential that we can use GATE. Okay? And we can also combine the results from the parallel computing. So this conclusion, group structure is prevalent in the scientific studies and decisions on both levels are important. And secondly, the reciprocity will exist in both between and within the group level and should be properly modeled. And then ignore the group structure will lead to an invalid and or less powerful inferential methods. Okay. So eventually, I just want to bring out this message, this picture, and which tells us this is a picture from the Lord of the Ring. And we know that this is behind this gate. Actually, they have them. minerals from the dwarf, and these are the gold, and which are precious treasure. Okay, so in order to get this treasure, and then what we need? We need a gate. So if we view nowadays we have the big data. In order to get the treasure from the big data, what do we need? We need a gate, the group assisted testing methods. Thank you.